All right, so we're still on section 3.3, number 35. It says f of x is x squared over x squared minus 9. And the directions are use the first derivative test to identify all relative extrema. What do we need to do? Correct answer is almost always find the derivative. F prime of x is bottom x squared minus 9 times the derivative of the top, 2x, minus the top, x squared, times the derivative of the bottom, which is 2x, all over bottom squared. We simplify that. What do you get when you simplify that? How about negative 18x over x squared minus 9 squared? Because when I distribute here, I would have 2x cubed, but over here I'm going to have a minus 2x cubed. Those are going to cancel out. The only thing that lives up on top is the minus 18x. What are my critical numbers? Where the derivative is 0, which is at x equals 0, because that'll make the top 0. And you also need to be concerned with spots where the derivative is undefined, which would mean bottom is 0. Where's the bottom 0? Plus or minus 3. Okay, but in this problem, 0 is a critical number. Plus and minus 3 are not critical numbers. Why not? Because you cannot plug plus and minus 3 into the original problem either, can you? So they're not critical numbers, but they're still numbers that you need to mark down on your number line. So when you draw your number line, you're going to mark negative 3, 0, and 3. So what's happening at plus and minus 3 in this original problem? If you were to draw the graph, you have asymptotes, correct? Because you have not 0 on top and 0 on bottom if you plug in 3 or negative 3. So we have asymptotes. So there are places where the function is undefined, there are places where the derivative is undefined. We still mark those on our number line. Okay, what's your favorite number bigger than 3?
4.
4. I plug 4 in. The top is going to be negative 18 times 4. That's a negative number. The bottom's going to be a positive number. The bottom's always going to be a positive number, isn't it? Because it's the whole thing squared. So if I plug in 4, I've got negative over positive. That's negative. Decreasing there. Favorite number between 0 and 3? 2. If I plug 2 in, I get a negative number over a positive number. That's still negative. Still decreasing. Favorite number between negative 3 and 0? Negative 1. When I plug negative 1 in, I get 18 on top. And I always get a positive number on bottom. Positive over positive is positive. And finally, favorite number smaller than negative 3? Negative 28. If I plug negative 28 in, negative 18 times negative 28, it's a pretty big number, but it's positive. I know that. My bottom is positive. Positive divided by positive is positive.
So the only point at 0?
So the only critical number is 0. And what's happening at 0? Do we have a minimum or a maximum? We have a maximum because the graph is going up, then it comes down. So our answer would be max, relative max, at, if x is 0, then y is also 0, because I would take 0, plug it into the original problem. I would get 0. It doesn't ask for this, but I'm going to write it down anyway. This function, we would say this function is increasing for x is bigger than 0, but x cannot be 3. And we would say it's decreasing. Oops, I got that wrong, don't I? Increasing, x is less than 0. That's why the arrows are up. X cannot equal negative 3. Decreasing when x is bigger than 0, but x cannot be 3. So using the first derivative test not only tells us about minimums and maximums, it also tells us about increasing and decreasing. I can. Y equals x squared divided by x squared. All messed up now here. X squared minus 9, there we go. Doesn't show up very well. There we go. So you can see we have the asymptotes at plus and minus 3, like we knew we did. And you can see it looks like at 0, 0, there is a relative maximum. Is it the absolute maximum? No, definitely not. Right, it certainly goes up higher over here, up towards infinity. Other questions? All right, today then, we move to section 3.4. No, but I don't think there will be any piecewise functions in on your exam. Were there some in the homework? Yeah. Piecewise function shouldn't be a big deal. How do you find the derivative of a piecewise function? You just find the derivative of each piece. That's all. And then you always have a problem at the spot where they come together. So that's usually a point of discontinuity or something, depending on the problem. All right, anyway, section 3.4. We're going to talk about concavity and the second derivative test. All right, so we're going to take a look at concavity. We have a function here. This is f of x. It's a cubic polynomial. You can see the definition of f of x there. And this is the tangent line to f of x. And right now it's a tangent line at x equals -10. And this is the slope of the tangent line. What we mean by concave down is we mean the derivative is decreasing. So right now I can see my derivative is 91. If I slide this to the right a little bit, you can see the derivative is getting smaller. You can see that in the number. The derivative's gone from 90-something to 60-something. And you can also see the slope. You can also see the tangent line is getting less steep, which tells you the derivative is getting smaller because that's the slope of the tangent line. I keep going. The derivative is still positive. The derivative here is about 19. But as you can see, the derivative continues to get smaller. As I keep moving along here, right in here, the derivative becomes 0. I can't quite hit the exact spot, but we have a relative maximum there. And then the derivative starts to become negative. But we can see the derivative is still getting smaller. -3, -4, so on and so forth, until right there, I think. Right there, our derivative hits -5, and I think that's our smallest value for our derivative. If I move over some more to the right, you can see the derivative now is getting bigger. It's going from, get it back to -5 here, -5, and -4, to negative. The derivative is still negative, but it's getting bigger. And then we reach our relative minimum. Now the derivative becomes positive, and it's bigger. So, we would say this function is concave down, going from -infinity. Well, this one only goes to -10, but you get the idea. Up until this point right here where the derivative is -5. So notice what it looks like. Concave down looks kind of like an upside down parabola. After x equals -2, this function becomes concave up. Kind of looks like a right side up parabola. Now, what are we going to do? Well, in this thing here, as I was sliding this, I kept saying the derivative is getting smaller. The derivative is decreasing. How do I determine when the derivative is decreasing? By looking at the second derivative. So to check concave down in this area and concave up in that area, we're going to be looking at the second derivative. So we say a function is concave up on an interval when its derivative is increasing. Now think back for a minute to section 3.3. When did we say a function was increasing? When is a function increasing? When its derivative is positive. When a function is increasing when its derivative is positive. So now I want to know when the derivative is increasing. How will I know when the derivative is increasing? The second derivative is positive. I.e., the second derivative is positive. So a function is increasing when its derivative is positive. A function is concave up when its second derivative is positive. And when, conversely, when is a function going to be concave down? When the second derivative is negative. F of x is concave down when the second derivative is negative. A point where concavity changes is called, anybody know what it's called when concavity changes? A point of inflection. So on that picture we had a minute ago, we saw where the derivative was, the derivative eventually was fixed at -5, and then it went from decreasing, the derivative was decreasing to the derivative was increasing. That would be our point of inflection. All right, so find a good problem here in section 3.4. Find the right page. F of x is x to the 5th minus 5x plus 2. So I'm going to ask you a lot of questions. Number 1, where is f of x increasing / decreasing? Classify all critical points. Where is f of x concave up and down? And 4, find all inflection points. So basically, in one problem, I can cover all of section 3.3 and all of section 3.4. Questions 1 and 2, that's what we did in section 3.3. 3 and 4, that's what we're doing today in 3.4. How do I find where f of x is increasing and decreasing? I find the derivative. So f prime of x is, what's the derivative? 5x to the 4th minus 5. What do I do with the derivative? Well, eventually I'm going to have to do it again, that's true. But right now I'm just working on increasing, decreasing. To find increasing, decreasing, I set the derivative equal to 0. And then I need to solve that equation. How would you solve that equation? Factor out of 5. 5 times x to the 4th minus 1 equals 0. Okay, then x to the 4th minus 1 equals 0. I don't really need the 5. How do I solve that? Add 1, and then what's the 4th root of 1? Plus and minus 1? You're almost correct. How many fourth roots of 1 are there? There's more than 1. There's more than 2. There are 4. If you have a 4th degree polynomial, how many answers should it have? It should have 4 answers. Nope. Some of them are going to be imaginary. That's correct. What you really want to do is you want to factor. This factors as x squared minus 1 and x squared plus 1. It's really a difference of squares. It's just kind of hidden. X squared minus 1 has 2 solutions. What are the solutions to x squared minus 1? X equals plus or minus 1, because that one you can factor as x plus 1, x minus 1. X squared plus 1, on the other hand, does not factor. So we get x equals negative 1, x equals 1. What are the answers to x squared plus 1 equals 0? I and negative I. Do we want those answers? No, we don't do complex numbers in this class. So you were correct. The answers are plus and minus 1. But there are 2 other answers that are hidden there. They're complex numbers. All right, I draw my number line. There's 1, there's negative 1. Favorite number bigger than 1? 2. 5 times 2 to the 4th minus 5. Positive number or negative number? Positive, increasing there. Favorite number between negative 1 and 1? 0. If I plug 0 in, I get negative 5. I can do that one in my head. And finally, I plug my favorite number smaller than negative 1 in. Negative 2. Negative 2 to the 4th times 5. That's something pretty positive. And then subtract 5, it's still going to be positive. Okay, so we have increasing. X is less than negative 1. X is bigger than 1. We have decreasing. Negative 1 is less than x is less than 1. And then we have a max at negative 1 comma. I need the y number. How do I find the y number? Plug it into the original. If I plug back up into the original, I'm going to have negative 1 plus 5 plus 2. 6. And I have a min at 1 comma 1 minus 5 plus 2. Negative 2. Alright, so there's the answers to problems 1 and 2. Find and classify all critical points. Determine increasing, decreasing. That's what we did back in the previous section. Now we do concave up, concave down. What do I need for concave up, concave down? I need the second derivative. F double prime of x is 20x cubed. Same idea. I now look for the points where the second derivative is 0 or the second derivative is undefined. Where is the second derivative 0 or undefined? Only one spot, 0. Okay, so 20x cubed equals 0 would give me x equals 0. We don't need to worry about undefined, do we? Because this was a polynomial. I draw my number line. I mark down 0. What's my favorite number bigger than 0? 1. If I plug 1 in, I get 20, which is a positive number. So I like to draw this for concave up. And then I pick my favorite number smaller than 0. Negative 1. Second derivative would be negative 20. So I draw concave down. So I would have concave up, x bigger than 0. Concave down, x less than 0. Do I have any points of inflection? At 0. Because it went from concave down to concave up. If this was concave down on this side and concave down on that side, that would not be called a point of inflection. So you're right, I need to find the corresponding y value. So I plug 0 into my original function. Forgot what my original function was because I changed my page. Where the heck did it go? Here it is. If I plug 0 into that function, I get 2. So we would say the point of inflection happens at 0, 2. Y equals, let's just graph that and see if it looks like what we believe. X to the 5th minus 5x plus 2. Does it look like we have a maximum at -1? Does it look like we have a minimum at +1? Yes. And does it look like 0, 2 is the inflection point? Yeah, it does, because it looks kind of like an upside down parabola for a while until it gets to right about there, and then it looks like a regular little parabola. So I do think that everything we did was correct. Questions on that?
Will we find lots of these problems in 3.4?
In 3.4, they're actually only asking you find where the function is concave up and concave down. I threw in the increasing, decreasing just for fun. Good practice. It will be like that on the test. On the test, I'm going to give you a problem, and I'm going to ask you to find all those things: increasing, decreasing, concave up, concave down, critical points, inflection points.
Can you not just, sorry,
Gary.
how many more sections do we have to go before next? We have, this is 3.4, we have 3.5, and then our next step.
I don't know. I'd have to look at the syllabus and see how many more sections there are. I think there's 2 more. I think there's 3.5, I think, is limits at infinity.
Yay.
It goes to 3.9. Oh, we got a long way to go. And 3.6 is graphing. So 3.6 is like everything we've done, 3.1 through 3.5, all combined together into one section. And then we've got something called Newton's method, something called differentials, something called optimization. Whatever all those things mean. Find out when we get there. It's looking like it's a long test. Does it say in the syllabus that we cover all of chapter 3?
Yeah, it goes right at 4.1 and then exam 3.
Okay. So we got a little ways to go yet. James.
If we ever do take a quiz or these problems are on a test, you're not just going to cover it all in one big go, right? Just in case we, per se, mess up the first part of it, that would make all of our answers for the second part of it probably incorrect.
Yes. So if you were to mess up the first derivative, you're correct. It would make your increasing, decreasing incorrect. It would make your second derivative incorrect. So what that means is those are a real pain in the neck to grade. Because if you screw up the first derivative, I then have to check everything from there to see if your work is correct from there or not. So I have to do the whole problem again to see, James dropped a minus sign right here. Did he do everything correct after that? So I kind of have to redo all it's a pain in the neck to grade. So don't make a mistake on the first derivative and make me have to work hard.
So it's consistency. So if you make a mistake, you can sort of that for the rest of this consistency.
Correct. Now here's what I've been known to do on a lot of problems. A lot of times I will do something like this. Let's say I were to give you f of x equals x squared plus 1 over x squared minus 1. If I were to give you a function like this, a lot of times I would tell you, here is the function, and then I would give you the first derivative, and I would give you the second derivative. And then from there I would say, now you tell me where it's increasing, decreasing, you classify all critical points. So if I'm going to give you a messy problem like this one, I'll probably give you the derivatives. If I'm going to give you an easy polynomial like I did in the last problem, then I'm going to assume you can find the derivative of that and do it correctly and not mess it up. Okay? So it's not as bad as you think. If it's a problem like this, I'm going to tell you, here's the first and second derivative. From there, you give me all the information. So let's do the same thing for this problem. Let's find the first derivative. Let's find the second derivative. Let's find the increasing, decreasing. Let's find the concave up, concave down. classify all critical points, find all inflection points. Lots and lots of stuff to do. Derivative. Bottom, x squared minus 1, times the derivative of the top, 2x, minus the top, x squared plus 1, times the derivative of the bottom, 2x, all divided by the bottom squared. And we need to simplify that, I think. We're going to have x squared minus 1 squared on bottom. What's going to happen on top? I don't think everything cancels, but I think some stuff cancels. I think I would have a 2x cubed and a minus 2x cubed. So I think the x cubes go away. And then I think I have a minus 2x and another minus 2x. So minus 2x and minus 2x makes minus 4x. So the first derivative actually wasn't so bad. It simplified okay. As long as we're here, let's keep going. Let's just go ahead and find the second derivative. And then we'll do all of our other stuff. F double prime of x is, again, I need to use the quotient rule. It's the bottom. X squared minus 1 squared times the derivative of the top, negative 4. Minus the top, minus negative 4x. Times the derivative of the bottom. For derivative of bottom, I need the chain rule. I bring the 2 down. X squared minus 1 to the 1. Times the derivative of the inside, that's 2x. All divided by x squared minus 1 to the 4th. Now I need to simplify that. Do you remember the good old days when you didn't have to simplify derivatives? Yeah, those days are gone. Got to simplify it. All right, how would you simplify this here second derivative? Take out? I heard something good. Take out a what? Not 3 of them, but I can take out 1 of them. Notice that I have an x squared minus 1 in every piece. Which means on top, I could factor out one of the x squared minus 1s, and then once I factor it out, what can I do with it? Reduce it with the one that's on bottom. So basically, I get to reduce one factor of x squared minus 1 everywhere. So this one reduces, and it's gone completely. This one reduces and becomes a power 1. And on bottom, we reduce, and that becomes a power 3. So that's the big thing you want to look for on these quotient rule problems. There will always be a common factor up on top like that, and always be something that will cancel with the bottom. All right, so now I think I just got to grind it out and see what I have. On bottom, I have x squared minus 1 cubed. Up on top, I'm just going to distribute here. Negative 4x squared plus 4. And then I have a minus and a minus, so those become pluses. 4x times 2 times 2x is 16x squared. So I think my second derivative, simplified down as much as I can, is 12x squared plus 4 over x squared minus 1 cubed. All right, so like I said, if I was going to be mean and I was going to give you this problem on the test, f of x equals x squared plus 1, I would say, here's your function, and I would tell you very specifically, here is your first derivative, all simplified down, and here is your second derivative, all simplified down. And that would save you a good 10 or 15 minutes on the test right there, not having to find those derivatives and simplify them. And then I don't worry about what James brought up, that is, if I messed up my first derivative, it messes up the whole rest of the problem. Here's a funny story. At least I found it funny at the time. When I was in graduate school, I was teaching Calculus 1. And there was a professor, his name was Dr. Herman, who wrote all the exams. So all I did is I kind of went in and taught, and he actually wrote all the exams and did all the homework and that stuff. And he did exactly this. He gave him a function where he gave him the original function, he gave him the derivative, he gave him the second derivative. Guess what? He made a mistake. He screwed up his first derivative, which messed up the whole rest of the problem and confused an awful lot of students. Because they would look at the graph, they would look at the answer that they got, and they would look at the graph on their calculator, and they didn't match. You know, the increasing, decreasing, concave up, it didn't match because Dr. Herman messed up his derivatives. So if I'm going to give them to you, I also have to be very, very careful and make sure I have my answers correct. I learned that lesson the hard way. Well, Dr. Herman learned it the hard way. All right, so anyway, now what do we do?
I hope it wasn't a complex problem.
It was similar to this. It was a problem with a fraction. And he literally dropped a minus sign somewhere, and he didn't check his work carefully. And it was ugly. All right, so increasing, decreasing. How do I do increasing, decreasing now? Set the first derivative to 0 and undefined. So here's my first derivative number line. What numbers do I mark on my number line for my first derivative? 0 and 1 and one more. Negative 1. 0 gives me 0 on top. 1 and negative 1 give me 0 on bottom. What's your favorite number bigger than 1? 2. If I plug 2 in, I get negative 8 over something positive because the bottom has a square in it. It's always positive. Negative 8 over positive is a negative number, decreasing. Favorite number between 0 and 1? A half would work. Negative 4 times a half is going to be negative. The bottom is always positive. Negative over positive is still negative. Favorite number between negative 1 and 0? Negative 1 half. Negative 4 times negative 1 half is going to be positive. The bottom is always positive. Positive over positive is positive. And finally, favorite number smaller than negative 1? Negative 2. That gives me 8 over something positive. That's positive. Okay, so my answer is increasing. X is less than 0, but X cannot be negative 1. How come X cannot be negative 1? It's not defined. If I plug negative 1 in, it's not in the domain of the original problem. Decreasing. X greater than 0. X does not equal 1. And what's happening at my critical point? I have a relative max at 0, comma. I got to plug 0 back up into my original function. I get negative 1. All right, so there's my first derivative information. There's all my increasing, decreasing, and relative min, relative max information. What's that? There was not a minimum. Nope. Because X cannot be 1 and X cannot be negative 1. And even if X could be 1, 1 still would not be a minimum, would it? Because the graph is coming down, it gets to 1, it keeps going down. So even if 1 were in the domain, 1 still would not be a minimum. It is possible for critical points to not be minimums and not be maximums. They can be nothing. That happens. All right, second derivative number line. What numbers do I mark on my number line for my second derivative? Well, let's start with the easy one. What numbers make the second derivative undefined? 1 and negative 1. What numbers make the second derivative 0? A third, no. Zero does not give me 0 on top. If I plug 0 in, I get 4 on top.
Oh, 1/9, right?
No. I'm going to give you a hint. It's a trick question. No real number would be the correct answer. 12x squared plus 4 equals 0? Correct. Because if I do 12x squared plus 4 equals 0, that's 12x squared equals negative 4. So x squared is negative 1/3. That's imaginary answers. So where is the second derivative equal to 0? Nowhere. for us. All right. Favorite number bigger than 1? 5. If I plug 5 in, I get 25 times 12 plus 4. That's positive. On bottom, I get 25 minus 1 cubed. Positive over positive is positive. Concave up. Favorite number between negative 1 and 1? 0. If I plug 0 in, I get 4 on top. I get negative 1 cubed on bottom. That's negative because negative 1 cubed is negative. Concave down. Favorite number smaller than negative 1? Negative 2. I get 12 times 4 plus 4. That's positive. 4 minus 1. Positive. Positive over positive is positive. Concave up there. So we have concave up, x less than negative 1, x bigger than 1. Concave down, x is in between negative 1 and 1. And what about inflection points? Negative 1 and 1 are not inflection points. What's wrong with negative 1 and 1? They do not plug into the original function. So, we do have spots where the concavity is changing, but they are not inflection points because they are not in the domain of the original function. So what do we have for inflection points? None. There are none. And that can happen. No inflection points. That can happen. Questions on that one?
There is actually inflection points, just not in the domain.
Well, what's happening at 1 and negative 1 on this problem? There are asymptotes. So no, there really aren't inflection points. The concavity changes, but it's not an inflection point because it's not a point on the graph. X squared plus 1.
Doesn't this graph go like this? Doesn't it go up and then spirals up through? Like it goes up and it comes up and it goes like that?
I don't know. It looks like
Exactly.
that. So you've got two pieces on the ends here that look kind of like hyperbolas, and then you've got a piece in the middle that looks kind of like an upside down parabola. But I do think we're right. I do think this area would be concave up, wouldn't it be? Would my derivative be increasing as I go along here? Absolutely. And here I do think we're concave down. My derivative here would be very steep, but as I move towards the right, my derivative would get less and less steep, so my derivative would be decreasing. Clearly, we do have a maximum right there at 0. And again, I think over here, our derivative would be increasing. Our derivative is negative, but I do think the derivative would be getting bigger. So I think we have all our information correct. Questions on that? All right, the last thing we have in this section is something called the second derivative test. What was the first derivative test? What was it? All right, so the first derivative test, we found the critical numbers, and then what did we do? We drew a number line to see if it was increasing and decreasing. And what did the first derivative tell us about the critical points? Whether they're maximum or minimums.
So does the second derivative test just
Nope. The second derivative test is also going to test to see if critical points are minimums or maximums. Okay, so it works like this. Let x equals c be a critical number of f of x. If the second derivative at c is positive, then f of x has a relative something. Would it be a maximum or a minimum? Second derivative is positive. Are you going to have a maximum or a minimum? Very good. Most people, when they first see that, they guess maximum. Second derivative is positive, they say maximum. But you're right, it is minimum. Because what I'm telling you is, we have a critical point at x equals c, but I'm telling you the second derivative is positive, which tells you the function is concave up. Which means, what has to happen at c? You've got to have a relative minimum. So if the second derivative is positive at c, then f of x has a relative minimum at x equals c. Conversely, what's going to happen if the second derivative is negative? Then you're going to be concave down, which means you're an upside down parabola, which means you have a relative max. If the second derivative at c is negative, then it has a relative maximum at x equals c. All right, so a typical homework problem is going to look like this. Oh, I didn't say this. What happens if the second derivative equals 0? Nope. Well, maybe it's an inflection point. It's possible. Nope. What happens if the second derivative is 0? The test doesn't give you any information. The test fails. What do you have to do? You got to go back and use the first derivative test. What if the second derivative is undefined? Then the test fails. You have to go back and use the first derivative test. All right. Let's see here. F of x equals the square root of x squared plus 1. The directions are classify critical points using the second derivative test. What do I need to do in order to classify the critical points using the second derivative test? First thing I need to do is find the derivative. Why do I need to find the derivative? Because I use that to find the second derivative. If I'm using the second derivative test, I clearly need to know the second derivative. Also, the first derivative gives me my critical points. All right, so we find the first derivative. I'm going to think of this as x squared plus 1 to the 1/2. So f prime of x is 1/2 times x squared plus 1 to the negative 1/2 times 2x. I'm going to rewrite that as 2x over x squared plus 1 to the 1/2, but that would be wrong. How about just x over x squared plus 1 to the 1/2? Why is it just x? The 2 and the 1/2 reduce each other. So there's my first derivative. Where are my critical numbers?
0, 1,
X equals 0, I agree with. 1 and negative 1, I do not agree with.
1.
1, I don't agree with, because if I plug 1 in, I get 1 plus 1 is 2 on bottom. Square root of negative 1. What's the square root of negative 1? I. Nothing we deal with. All right, so we only have one critical number. Well, if x is 0, I can plug that in right away, and I can tell you y is 1, correct? Now, what I want to know is the point 0, 1. Is it a minimum or is it a maximum? And this time I'm told very specifically, use the second derivative test. So I need to find the second derivative. F double prime of x is the bottom, x squared plus 1 to the 1/2.
Why is y 1?
Because I took 0 and I plugged it into my original function.
Oh, sorry, never mind.
That's okay. Second derivative. I have the bottom, x squared plus 1 to the 1/2, times the derivative of the top, that's 1. Minus the top, that's x. times the derivative of the bottom. That's going to be 1/2 x squared plus 1 to the minus 1/2 times 2x, all divided by the bottom squared. But the bottom, x squared plus 1 to the 1/2, that's 1/2 is really a square root. So when I square a square root, those cancel out, I just get x squared plus 1. Almost done. What do I do next? I'm not going to simplify. Because all I really need to do at this point is plug in my number. I'd much rather plug in my number and simplify with all numbers than I would with all the x's. So this is my personal opinion. I would not simplify my second derivative here. All I would do is plug in my number. F double prime at 0 is 1 minus 0 over 1, and that's very easy to simplify. You see why I don't waste my time simplifying? It's much easier to simplify when you just have numbers. My second derivative is 1, which is a positive number. So if my second derivative is positive, what does that tell me about my critical point? It's a relative minimum. So relative min at 0, 1. Now I have an obvious question for you. Why would you use the second derivative test? I mean, it seems to me as though back here where I had my derivative, it would be pretty easy to draw my number line, plug in a positive number, plug in a negative number, and use the first derivative test, and I'm pretty sure right now that I have a minimum right there. It's faster? Well, I think the first derivative test was faster. I think drawing that number line was much quicker than having to find this derivative and then plug in that number. And we got lucky that we plugged in 0. 0 made it really easy because it canceled out all of this stuff over here. If we'd had to plug in a half or something, it would have been a real mess, wouldn't it? No, it's no more accurate.
Why was the only critical number 0?
Because 0 gave me 0 on top, and the only thing that gave me 0 on bottom were complex numbers, I and negative I. We don't like complex numbers. So why use the second derivative test? The reality is, I only use the second derivative test when I'm doing work on a computer. Because once I find the derivative and set it equal to 0, I can very easily ask Wolfram alpha, evaluate the second derivative at 0. And it will do it for me. In that case, I then don't have to draw this number line and draw these arrows. I can just say, Wolfram alpha, tell me second derivative at 0. It will tell me the answer is 1, which will tell me I have a relative minimum. My personal opinion is I think that's the only time the second derivative test is better, is when you have a computer algebra system and you can ask it to find the second derivative and plug in the number for you. And then I think it's quicker and easier. Otherwise, in reality, I think the first derivative test is always easier. That's my opinion. Questions about that? All right, then I'll see you tomorrow.